In the last few videos, we've met the ideas of tangent plane and differential, written out here. And previously we met the chain rule. Let r of t equal x of ti plus y of tj be a path in the domain, and then dz dt is equal to fx times dx dt plus fy dy dt. And I wanted to point out the similarity between our chain rule and this idea of differential. That this is a derivative in its differential form, and it simply is a formulation of the chain rule if I drop the dt's. Another way to think about that is I could think about multiplying both sides of this by dt. Now that's not a formal derivation of the chain rule coming from the differential, but it does give us a justification for it, thinking about the definition of differential. The last thing I want to tie together is this idea of differentiability. In Calc 1, we're told a function is differentiable if its linearization does a good job of approximating the function. And sometimes that's written as the actual change in y is equal to f prime of x naught times a change in x plus an error term, which is epsilon times delta x, and we're told our function is called differentiable if epsilon goes to 0 whenever delta x goes to 0. The corresponding idea for us is that a function on two variables, z equals f of x comma y, is differentiable at a point p naught, which is x naught comma y naught, if both partials exist at that point, and delta z, the actual change in z, is equal to this statement, which is a differential statement plus two error terms, epsilon 1 times delta x plus epsilon 2 times delta y. Well, our function is called differentiable if both epsilons go to 0 when delta x and delta y both go to 0. This is really saying that the difference between the actual change in z and the differential approximation of the change in z are nearly the same as long as our points are close. The change in x and the change in y is going to 0 means these 2 points are getting closer and closer together. When a function z equals f of xy is differentiable for all of the points in its domain, we call it a differentiable function, and we call its graph smooth.